Let's move on with this. Now, once we have the Fourier series um, in a better understanding, let's take a look to the Fourier transform. Fourier series and Fourier transform are not the same. The principle of the mathematical expression or development for the Fourier series and the Fourier transforms, it comes from the same method, but the applications of the Fourier series and the Fourier transforms are different. The Fourier series, the topic that we already covered, are applicable for periodic functions only. If you know, the periodic functions are those others equal to 2 times pi times the frequency. So it means that every certain amount of cycles that add multiple of pi, they repeat evenly time after time. And that's the main requirement in this case for a function to be eligible to apply the Fourier series. So it has to be a periodic function. But what happens if the signal or the of the function that we are working with are not periodic? Well, if this function or signal is not periodic, then we will apply the Fourier transforms. See, the Fourier series are applicable for periodic functions only, and the Fourier transforms is the same, but this is applicable for non-periodic functions. In the case of the Fourier series, we are working or we are dealing with, as we saw in our last lecture, that we are dealing with some signal that is like this. Let's say that this is a square signal, and we are working with the entire shape or envelope of this signal from one instant of time to one instant of time. So we are analyzing by the Fourier series all these uh, different cycles of the signal or of the function. In the case of the Fourier transform, it's not the same as this one. In the case of the Fourier transform, we are analyzing only one single event or one single spike or period of this function. Why? Because in this case, we are dealing with something that is not periodic. So this is the main difference between the Fourier series and the Fourier transform. Fourier series are applicable to periodic functions, which is a multiple of phi in frequency, and Fourier transform is the same, but it works out for the non-periodic functions. Okay, um, Fourier series and Fourier transforms switch our signals or functions from the time domain to the frequency domain. So we are transforming our signal or our function. If we have something that is working in the domain of time, some f of t, if you remember when we work with the Laplace transform, we uh, switch this equation or this function of this mathematical expression from the domain of time to the S domain. If you remember, we were working with the S domain in the Laplace transform. In the Fourier series, we are working and switching from the domain of time to the domain of f. W, which is um, something in relation to the frequency domain. So these two are part of the frequency domain, but the difference is that in this case, for Fourier series, we are using trigonometric expressions and we are adding all those trigonometric functions together to get an equation or a set of equations that is a representation of the original signal, but in terms of a sum of trigonometric terms. So you and we were working in the back in the last video lectures on the standard equation for the Fourier series. Fourier series and Fourier transform are almost the same set of equations, but in this case, one of the other differences that works with the Fourier transform is now that the Fourier transform is working specifically in the complex domain. So there is a standard sinusoidal and cosine Fourier series, and if we apply or we plug the Euler's formula, we can get out of the trigonometric part of the Fourier series the complex form. If you know this part over here, which is j is equal to the square root of minus 1, which is equal to I, which is the complex number, but this is applicable more for math. And because this symbol is an identification for current in electrical or electronic engineering, that's the reason why in these calculations we are not using I as a representation of the complex number. We are using J. So electrical and electronic engineers, they work with J, and most mathematicians, when they are applying this to something that is not related to any signal or any voltage or current, they usually apply I as the number or notation to identify this expression. Okay, so J equals the square root of minus 1 equals I as a complex a number. Okay, so we can transform that the both of that pair of trigonometric functions, which were the cosine and the sine of any variable. You will remember there is an Euler's formula that we can express the trigonometric sum of those sine and cosine functions in terms of a complex number. So if you find out, we can see that the Euler number up to the j some integer multiplied by the frequency, which is omega times t, this is equal to that expression that was part of the second expression of the Fourier original series, which were the sine and the cosine of the variable times omega t. So we transform that and we plug the Euler's formula to the trigonometric part of the Fourier series, we will come up with this. This part over here is equal to that sum of cosine and sines in the Fourier series. And in this case, J represents the complex number, N represents an integer, which is here, is the amount of the variable that we are multiplying the frequency, which is the omega, t times dt. And in this case, C sub n, which is this one, are the same coefficients that we were calculating in the past, but in this case, these coefficients are working in the complex plane. So this is the complex form of the Fourier transform. And just to let you know, this is a brief introduction of this. We don't have plenty time to work this in detail, but I don't want you to get lost in this. So please take note. This is the pair of equations to calculate the Fourier transforms. And this is the equation number 1, and this is the equation number 2. And my recommendation is please take note of this because you are going to use it by the rest of your lives, especially if you are going to work in design. Please take note of this and please don't forget it. The people that will forget these equations are people who are selling cars or they are working in another descriptions, but as an electronic, robotic, or mechatronic engineers, please don't forget this pair of equations. The first one, this is the notation for the Fourier transform. If you remember the Laplace were something like this, but Fourier is kind of italic or Roman F. So this is the Fourier transform notation of any function f of t. Let me write here the parentheses that I'm missing. The Fourier of any function that is in the time domain will be equal to f capital F. This capital F in some textbooks it means the same that this, because in some textbooks you will not find this stylized F. So the Fourier transform of any function f of t will be equal to this f capital F of j times omega. And remember that j is the complex number. And then that will be equal to the integral from minus infinity to infinity. And this is only the general expression because in some cases you will find, for example, you need to set the Fourier transform of this signal, which the number is maybe minus 2 times pi, and this is 2, no, over t, minus 2 over t and plus 2 over t. So the region of integration is between this point and this point, and we are going to change this minus infinity plus infinity with this domain that is showing here. Why? Because we are integrating this part and we are transforming this into a complex exponential trigonometric expression. And what we are going to get out of this? Well, this is the f of t times the Euler number to the minus j omega t times dt. So this is the integral to obtain the Fourier transform of any function f of t. Okay, and this is the equation number one. And the inverse equation for the Fourier transform, if you remember where we're working with Laplace, the inverse Laplace was something like this, L to the minus 1, which is the inverse Laplace. So the inverse Fourier transform is equal to some function g. G, in this case, I'm using this letter, and some textbooks they do because they don't want you to get confused. This GGW is the same as the Fourier transform that we were working in the past. So this is a representation of the Fourier transform, and we are going to apply the inverse transform to this. So that's going to be equal to some function g of t, and the mathematical expression to calculate the inverse transform of the Fourier is 1 over 2 times pi times the integral from minus infinity to infinity of the Fourier transform, which is in this case is represented by the letter g, g times j omega that multiplies the Euler number up to the j omega t d omega. So you see here we are doing some kind of inverse calculation because here we have a function that is in the domain of t, which is the time. And when we have the Fourier transform, we have a Fourier transform working in the frequency domain, which is the W, or in this case, omega. So this is the direct for Fourier transform, and this is the inverse for Fourier transform. Please take note of these two integrals. Don't forget it. Highlight it with a marker or something. maybe in the future who are going to use it. And let's see to work out some examples in our next class. So this is a brief summary of what the Fourier transform are about. I hope this is clear and understandable for you. But if you have any questions or comments, feel free to let me know, and I will be aware of your comments and questions so we can solve it. And please stay safe.